Alignment torque, also called mutual torque. If you followed the series, you've actually been looking at consequences of this mechanism since episode 1, without me naming it directly. Here's the formal idea. Alignment torque is produced when the mutual flux linking a magnet and a coil, or linking two separate coils, changes as a function of position. In plain terms, it's the torque that comes from magnets and currents working together, not fighting some internal reluctance. This is the real motor torque, the one your BLDC or PMSM is actually built to produce. Today, we open up where it comes from and how it connects to everything else in this series. Torque in an electric machine is produced by exactly two mechanisms, and it's worth being precise about the difference. Mutual torque comes from mutual inductance, changing with position, that's alignment torque. Reluctance torque comes from self-inductance, changing with position. Most motor types commit to just one of these. Induction motors, brush, and brushless DC motors, and synchronous motors are all designed around mutual torque. Switched reluctance motors, as the name suggests, are built entirely around reluctance torque instead. Here's the connection back to episode 1. In a motor designed for mutual torque, reluctance torque is usually parasitic, unwanted. Cogging torque, which we covered first in this series, is exactly that. Reluctance torque sneaking into a motor that's supposed to run on mutual torque alone. There's a beautifully simple sign rule underneath all of this, and you already know it intuitively. Positive torque acts to increase the mutual coupling between a magnet and a coil whenever their fluxes add together. Negative torque acts to decrease that coupling whenever the fluxes oppose each other. Strip away the calculus, and this is just the oldest axiom in magnetism restated with precision. Opposite poles attract like poles repel. Every alignment torque calculation you'll ever do in motor design traces back to this one rule, playing out between the rotor's magnet poles and the field produced by the stator's current-carrying coils. Here's the equation that quietly runs through this entire series. For any device producing mutual torque, electrical input power always equals mechanical output power. Back EMF times current equals torque times mechanical speed. Know any two of those four quantities, back EMF, current, torque, or speed, and this equation hands you the other two. But it's not just a bookkeeping tool. This is exactly where the design insight from the torque constant video comes from. The idea that a high back EMF at low current is preferred over a low back EMF at high current for the exact same mechanical power output. That preference isn't a rule of thumb. It falls directly out of this one equation, because minimizing current directly minimizes the burden on the power electronics driving the motor. Let's bring this back together. Alignment torque is the goal. It's what turns electrical power into useful mechanical work in a BLDC or PMSM. Reluctance torque, in this same motor, is usually the enemy, showing up as cogging and other ripple sources that designers spend real effort minimizing. And here's how this episode actually ties the whole series together. Episode 1, Cogging Torque, was the parasitic reluctance torque this framework predicts. Episodes 2 through 6, back EMF, the back EMF constant, the torque constant, the motor constant, and armature reaction, all describe consequences of mutual flux linking the magnet to the coil. Alignment torque was never a separate topic. It was the mechanism underneath everything this series has covered so far.